Okay, we're going to continue with last week's lecture. Last week was quite heavily intensive from my perspective, trying to introduce the degree of topic, the terminology, some basic formulae we needed. This week I want it to be a bit more you engage and doing lots of questions this week. So by the time we finish this lecture, I'm hoping that you'll be fairly confident in solving gear problems, simple gear trains, compound gear trains, and then have a good grounding for what we need to do next week, which is the epicyclic gear trains. All right, so everything we're doing today is kind of underpinning where we're going next week. So a good grounding today is really useful. What you're seeing on the screen is an extract from the formulae sheet I gave you. I'll backtrack a little bit to last week's work, just showing you some of the formulas we derived. So if we just go through these briefly, and we'll be using quite a few of these in today's session. So basic terminology we're talking about, aren't we here? So don't forget that velocity ratio and gear ratio are interchangeable terms. If the question asks you for velocity ratio, they mean gear ratio. It's the same term. Usually symbol G in most textbooks. So our basic definition we had for working out the gear ratio was the speed of the driver, I've called that omega A here, driver gear, divided by the speed of the driven, which is omega B, this gear here. That's a basic relationship we had. We did show that the velocity ratio can also be defined as the number of teeth on the driven gear, and B, I'm showing it there, divided by number of teeth on the driving gear. That's another relationship we formed. And also this relationship here, which is just to do with geometry, the center distance, C, is the radius of gear A added to the radius of gear B. So just add in sort of the radius of gear A to the radius of gear B, gives a center distance. Or if you want to put it in terms of diameters, that would be half the diameter of gear A added to the diameter of gear B. That's a geometrical relationship, which is quite useful. So that was finding the center distance C between the gears. And again, these from last week's some basic definitions we talked about, where we defined diametrical pitch. Capital P was a number of teeth on the gear divided by the pitch circle diameter of a gear, labelled D. We mentioned the module last week, lowercase m. That's quite a useful characteristic of a gear. The module is actually the reciprocal of the diametrical pitch. It's D upon N in this case. Pitch circle circumference, another useful quantity that relates to circumference around the entire disk at this location. So here, this would be the pitch circle circumference in our circle, and that's simply pi multiplied by d. D is the pitch circle diameter. The circular pitch we mentioned last week, lowercase p this time, that's the pitch circle circumference divided by the number of teeth on a particular gear. So pitch circle circumference is pi d, number of teeth on the gear is n. Through here, that's a circular pitch there, okay? That's kind of useful between the beginning of that tuff and the beginning of the next tuff. It's a quite useful relationship. I know we mentioned pitch circle circumference, PCC. That can also be the circular pitch times the number of teeth, another way of saying defining the pitch circle circumference. So those basic relationships, you'll see they'll start to crop up in some of the questions and use the information in the question to help us solve the problem. So be aware of those. So we started off talking about simple gear trains last week, when the velocity ratio G can be defined as the speed of the driver or speed of the driven. Here, I've got here, but notice a reciprocal there. Speed of the driver over speed of the driven, number of teeth of the driven over number of teeth of the driver, diameter of the driven over diameter of the driver. Notice the relationship there. But again, a very useful relationship. Again, it crops up in lots of questions. If we consider compound gear trains, so the top diagram is a simple gear train. This is a compound gear train we mentioned last week, where we have a pair of gears here and also a pair of gears over here. And then these two gears, the B and C, are on the same shaft here. So that makes them a compound gear. Slightly more complicated to find the velocity ratio. So to find the velocity ratio G, it's the product of the number of teeth on the driven gears divided by the product of number of teeth on the driving gears. Okay, so in this particular case here, looking at the sketch below, if we want to find G, and it would be number of teeth on the driven gears. So in this case, B is driven and D is driven. So it will be B multiplied by the D divided by the number of teeth on the driving gears, which is the A multiplied by C there. Okay, so it's a little formula. Of course, we could have more complicated compound gear trains than that. We did look at a few last week where that equation becomes slightly elongated. And again, some geometrical relationships, which we'll look at later on, but we've already defined one of them on the previous slide. This one here, diameter of gear A added to the diameter of gear B can be written as the diameter of gear C added to the diameter of gear D for compound trains. That's true. It's really talking about the centre distance here as well for the different gears. And that can, of course, be written in terms of number of teeth as above. So we've got the NB upon NA, and that relationship relates to the diameters. Another relationship we'll look at later on, which is very similar to the one above, and that relates to the number of teeth on the gears on, say, this train here in this particular instance, multiplied by the module of the gears there. The modules for those gears must be the same if they're going to mesh, because that relates to the pitch of the gears. But we can also equate that to the number of teeth on this gear train here multiplied by its module. So the modules could be different between A and B and D and C. They must be the same for A and B for meshing. They must be the same for D and C for meshing. We can use that geometrical constraint to help us extract information from the question and help solve the problems. So you'll see some of these relationships later on in the presentation. And also I'm going to introduce, before we finish today, some formulae related to torque, power and efficiencies. We've not mentioned those really yet. We just really focused on velocity ratios. But we will have to look at torques that are generated. So we'll have an equilibrium equation. This is the input torque added to the output torque plus what's called a holding down torque or a casing torque. That should be 0 for equilibrium, we'll see later on. And we can also write that in terms of power as torque times angular velocity, if you remember, is power. So we'll also be writing that in terms of a power equation. And we'll mention the efficiency of a gear system, symbol eta here, which is the output power divided by the input power. Or if you like, in terms of torque and angular velocity, it's the output torque multiplied by the output angular velocity divided by the input torque times the input angular velocity. Notice the symbol change there. I've got a lowercase omega here, uppercase omega here. In actual fact, with a lot of the questions today, we can interchange RPM and radians per second, but we do need to be careful. There are certain instances when your angular velocity must be in radians per second. But when we're talking about ratios between inputs and outputs, we can get away with using RPMs in the calculations. So we just need to be careful with that. So I'm going to start with question 4A on your sheets. So in this case, we've actually got no diagram. So in a minute, you're going to have to try and sketch a diagram of the gear system. So let's read the information carefully here and see if we can digest it and then extract what we need to form the gear train. So we've got an input pulley of a certain lathe headstock, and that revolves at 800 RPM. In a particular gear, so they're talking about the gears can be changed on this lathe, but in a particular gear, an 18-tooth pinion wheel, that's a small gear, is fixed on the same shaft as the pulley. Okay, so it's like a compound gear, if you like, with the pulley, you could think of it that way. And that gear meshes with a 130-tooth gear wheel, which is key to what they call an intermediate shaft. Just a bit of terminology there. Also on the keyed onto the intermediate shaft is an 85-tooth gear wheel, and that meshes with a gear wheel having 100 teeth. So that's splined to the lathe spindle, which will be the output. Okay, so what we've got to do is try and find the speed of the lathe spindle in this particular gear that they're considering here. Okay, so what I want you to try and do is to see if you can sketch a compound gear train. This will be, it's a fairly smallish train, given the information in the question. I'll leave that with you for a minute. Okay, there's my sketch then of what I've got. I don't know how it compares to yours. So from the question, we've got this pulley here on 800 RPM, and we're told that that's joined on the shaft, same shaft as an 18-tooth gear wheel. I've called these A, B, C, and D, just give them labels. So my first gear there is A, and then we have the 18-tooth gear wheel is meshing with a 130-tooth gear wheel. I've called that B here. So I've got a train here, and then on the same shaft is the 130-tooth gear wheel. We've got this 85-tooth gear wheel. I've called that C here. So this shaft, another gear that meshes with the 100-tooth gear wheel there, and that drives the spindle. So that's a little gear train we're talking about here. So the next question is, you've got to find the lathe spindle speed. So the first thing to do is find the gear ratio, the velocity ratio, as we did last week. So again, can I let you consider that? You'll be using your formula for G is the product of the number of teeth on the driven gears over the product number of teeth on the driving gears. You've got all the teeth given to you. So can I let you go through the process of working out the gear ratio here? And then from the gear ratio, of course, you can find the output speed because you know the puller's input speed. One thing that's difficult with online lectures as opposed to in classes is pacing the lecture. I have no idea about pacing, whether I go too slow or too fast. So I do need a little bit of feedback. If you just sort of type in your chat or something that you're okay, that would help me greatly because I just don't know out here. I could be talking to myself, of course, which is the first sign of madness apparently, isn't it? So on my little diagram is my solution here, my diagram here. When you're trying to find the direction of the output gear to the input gear, just use velocity arrows. You can see them over here if I highlight them. So if I assume my pulley is going in the clockwise direction and gear A would go into a clockwise direction, that would mean that gear B would go in an anti-clockwise direction, and so gear C on the same shaft would go anti-clockwise direction, and that means then gear D going in the clockwise direction. So the lathe spindle's going in the clockwise direction as well. Okay, so the output and input in this particular case has the same sense. Okay, this one's a bit trickier, this one. I like this question actually. It's quite, it gets you a bit thinking this. You've got to find, in this case, the gear ratio basically, but you've also got to find the sense of the output gear to the input gear. And it looks pretty horrendous, that, doesn't it? But it's a kind of slight insight into what we're going to have next week. We've got a gear train, that's shown. A combination of both simple and compound gear trains. We've got to calculate the gear ratio of the train, and then we've got to find is the direction of the output gear in the same sense as the input gear. And I notice they've left that as a question mark, so no help there. And we've got the gear ratio in the question. Now, just one thing to be careful of here. We've got what's called this internal teeth. Can you see that there? Now, what that is, I've got a picture. I don't know if this helps, this kind of picture. It's an internal gear ring. We've got gear teeth cut on the inside of a ring. And when we're looking at epicyclists next week, you'll see that we'll have these kind of gear rings in our analysis. From today's point of view, all I'm really interested in is just the way it affects the rotations here. And I tried to put this little diagram together. I don't know if this helps you. This little note at the bottom on the left hand side here. It should be in your notes as well, where I've got an internal gear wheel shown as ring as such. I call it a ring gear or something like that. And notice that if we look at the senses here, the sense of this gear that would be, say, gear 4, for example, that would be contacting it, is going, shown here, is going in a clockwise direction. So notice that the ring itself will also go in a clockwise direction. But then the gear the other side will go in an anti-clockwise direction. So just be careful that when we're working out our directions in a moment, that the gear 4, if that was going in a clockwise direction, then that would push the ring here, gear 5. That would also go in the same direction as gear 4, okay? Just be careful of that when you come to do your senses in the moment of what you're doing. But the first thing is to calculate the gear ratio, and that's going to be a bit of fun here. Again, it's back to using your formula for the G as a product of the number of driven teeth over the product number of the driving teeth. The same kind of formula here. But you need to think through very carefully here what's driving and what's driven. Again, I'd like to let you have a little look at that for a moment before I show the solution. See what you can do to work out the gear ratio. We thought it's 2 in the question. Gear ratio of 2, it says here. So see if you get 2 for your gear ratio. Can I let you have a little play with that for a moment? And then we'll look at the velocity arrows, effectively trying to find the direction of the output gear to the input gear. Okay, over to you. Well, let's go through and have a just quick chat about it first of all. So let's look at our driving and driven gears, see if we agree with this. So obviously 1 will be driving, 2 is driven, 3 driving, 3 is driving 4, and 4 is driving on 5. So 4 is going to be like an idler gear. And then 5 is driving on 6. And then 7 is driving on 8, and 8 is driving on 9. So 8 again looks like another idler gear. So we've got a couple of idler gears there in our gear train. So if we put them in, they should cancel from your equation because they'll be on the top and the bottom of the equation. Here's my solution. So I put all my gears in to begin with, but of course some of them are idler gears. So the top of the line you should get, top of your equation, I've got N2 multiplied by N6 multiplied by N9. And then that's divided by the N1 multiplied by N3 multiplied by N7. Because 5 is being driven by 4, but 5 is also driving 6. You see? So effectively 5 is like an idler gear really. It's not affecting the gear ratio. It's the driving and it's driven. So you put it in, like I did put it in up on my little diagram here. If I put it in, it will cancel out because I've got on the top there N5 because it's being driven, but also N5 is driving, so it cancels itself out. And you should find the same with 8 as well, because 8 is being driven by 7, but 8 is also driving 9. So 8, I put it in on my top line, but it's cancelled with the term on the bottom line. So you see that they cancel out. N4 is another one. N4 is being driven by 3, but N4 is driving 5. So again, N4 will cancel out. Okay. So just N2, N6, N9 on the top line, N1, N3, N7 on the bottom line. And that, when you do the numbers on that, it should come out to be 2 to 1 ratio, basically. Ratio 2 to 1. It's a reduction gearbox. And the velocity arrows are fun. Look at the velocity arrows, shall we see what we can do with those? For a bit of clarity. So let's say the input gear is a positive. I'll do it in red here, so positive. That will make gear 2 become a negative sense, and then gear 3 will be negative sense, go on the same shaft. That would make gear 4 go in a positive sense. And gear 5, notice that little diagram, that will also be in a positive sense on that one, which will make gear 6 will be in a positive sense. Gear 7 will be in a positive sense. Gear 8 will be in a negative sense. And gear 9 will be in a positive sense. So same direction between the input and the output. Question 6 I'd like you to have a go at. This time you have got the diagram. It's a complicated diagram, doesn't it, here? But again, if you break it down like you have the previous question, it's a very similar kind of question. It does bring into play, though, the table. We've got a table in this particular case, a rack, to consider also. A planar machine table is shown within the sketch. We've got a drive-in pulley is 300 revs per minute, driven by an electric motor. So the drive-in pulley, that'll be this one here, 300 RPM. Key to the same shaft as the drive-in pulley, we've got a 25 pinion gear there. That's driving an 85 tooth gear wheel. So pinion gear is that one there, which will be this one here. So that's my 85 tooth gear wheel, which is fixed on the same shaft to a 35 tooth pinion. So 35 tooth pinion, which will be this one here, which is this one up here. Multicolored effect here. This pinion then drives a gear that has 130 teeth on it. So here's my 130 teeth gear wheel, this one here. Fixed to the same shaft as this gear is a 30 tooth pinion. So that'll be the 30 tooth pinion here, 30 tooth pinion here. That drives what's called a bull wheel, and the bull wheel has 75 teeth. So the bull wheel, 75 teeth, that one there is the bull wheel. Okay, so we end up messing with a rack, given the pitch of the rack teeth, 25mm. That could be useful later on. Okay, so multiple color coded there for you. So the first step in the process is to find the speed of the bull wheel. That's the output shaft in this case. So again, that's going to be working out the velocity ratio first of all. We've got the input speed at 300 RPM, so we can find the output speed. So part A should be okay. And then to find the direction of the rotation of the bull wheel, part B, we can use our velocity arrows again. Part C goes back to what we did last week. We've got to find the speed of the table in this case. When it says the speed of the table, it's got a cutting speed, it's got a linear velocity. So obviously we'll have to relate our angular velocity to our linear velocity. So that V equals omega R equation springs to mind there, relating linear velocity to angular velocity. And then to find how far the table travels in 5 seconds, once we've got the linear velocity, we're just going to multiply it by the time, and we'll get the distance travelled. Answers are shown in the brackets. Can I let you have a play, see what you can do with that question for parts A, B, C, and D? Okay, just a little check for you along the way, intermediate check. That was my gear ratio. You can put it into decimals if you want to, 31.57 to 1 I've got also, but often it's left in a fraction form, so feel free to leave it like that if you want to. There's my gear ratio. Does that help there? So my gear ratio, so I've got in this case my driven is going to be gear B. B's are driven. Gear D is driven, and gear F is driven. So my driven gears, my driving gears, I've got gear A is driving, C driving, and E driving. Remain with a 221 upon 7. So input shaft rotates 221 revs, or output shaft rotates 7 revs. Well, there's my diagram, I've lost the arrow. So if I say my input gear is going in a positive sense, shown on my diagram there. So positive for the pulley, positive for the gear A. Gear A is positive, so it goes negative for B, negative for C on the same shaft, goes positive for D, positive for E on the same shaft, and then negative for F. So opposite sense to the input. Part C, calculate speed of the table. I've calculated the speed of gear F because I've got the gear ratio and I can find the speed of gear F. So my speed of gear F and the gear ratio, the input speed over the output speed, A upon F in this case, 22 upon 7. I've used the decimal there, but I get 9.5 RPM for my final speed for gear F. So you need the speed of that final gear. That meshes with the rack. Now they've asked us to find the speed of the table, which of course is a linear velocity from angular motion of the gear F to linear motion of the rack. So I can certainly see the V equals omega R we're going to need in a moment. We've got the omega. We can work out the omega. We've got 9.5 RPM. I can work that in terms of radians per second. But what we need to find is the radius. So the way I'm thinking, this is sort of my thinking steps at the moment. I'm thinking I'm going to use this formula here, V is equal to omega R. I've kind of got my omega here, but I need to put it into radians per second to use it here. So I'm going to have to multiply that value by the 2 pi upon 60 because we've got to use radians per second here. But I don't have the radius of the gear wheel at the moment. So I need a relationship that's going to help me find the diameter probably first of all, and then the radius. So is there anything in the question that might give us a bit of a hint as to how we know the pitch is, it was 25 millimeters, I think, so I'll put that in meters. So we're given that, the pitch. Now, how can I relate pitch to diameter, number of teeth? That's the way I'll be thinking now. I know number of teeth on the output gear is given in the question. I've got these 75 teeth. I've got the pitch of the gear. Was there any way I can find the diameter from our relationships we've looked at before? These really little formula sheets are quite useful. You can sort of browse through your formula and see, well, what's relevant in this case? We know the pitch, we know the number of teeth, we need to find the diameter. So we know that the circular pitch is going to be pi d upon n. I think what we've got here, we've got the number of teeth because I can see it in the question. We've got the pitch given to us in the question, so I can rearrange the equation to find the diameter. So that's my approach. I'll find the diameter of the bull wheel, that's gear wheel F, as I've labelled it here. Then of course I can find the radius, and once I've got the radius I can go back into this equation here, and I can find the velocity of the rack. Okay, again, can I let you have a little play with that, see if you can think your way through that. Have a little go at that, see what you can get for your diameter. Okay, so a little check there. The diameter I get is 0.597 meters. Now you can find your radius from that, and from that you can find your linear velocity, and then you can find the distance travelled in 5 seconds, which I think is the last part of the question for us to review. And I get 1.5 meters for that. Okay, there's my calculations there. Using the circular pitch that we were given in the question, we've got that stated in the question. That's equal to pi d divided by n. So I just transpose the equation. D is equal to the number of teeth multiplied by the pitch divided by pi. Transposition there. But in the figures, the diameter is 0.597 meters. Then using this relationship, really useful relationship. This one, always sort of keep that in mind. V is equal to omega r is a really useful relationship relating angular velocity and linear velocity here. Must always though convert though, so that 9.5 RPM must be converted into radians per second. I get nominally 1 rads per second there, approximately 1 radian per second. Our radius is just half the diameter, so 0.298 meters. So V is equal to omega r, V is equal to the 1 times the 0.298. I said approximately 0.3 meters per second. The last part, you've got to find the linear distance travelled in 5 seconds. So distance is velocity times time. Time was 5 seconds, so in this case the distance travelled 0.3 meters per second times 5 seconds, 1.5 meters I get. What I would like you to do is to have a go at question 7 actually. Nice short little question here, but it's mixing diameters and teeth. But that shouldn't be a problem if you understand your relationships now between diameters, teeth and speeds. Okay, so question 7a. With reference to the information shown, we've got to calculate the speed of shaft X, which is the output shaft here, in revs per second. When, we're given some information, now be careful here, we've got the diameter of 1, so diameter 1 is 80 millimeters. We've got the diameter of 2 is 160 millimeters. And then we've got, they've called it D there, but actually it's not quite D, it's N really. But anyway, D3, they call that, is 120 teeth. So we've got 120 teeth on gear 3. And on gear 4, D4, we've got 200 teeth. Okay, so they're mixing and matching here, but as I said, if you understand your relationships, it's not really a problem to work out the gear ratio. We've got the speed of the motor is 1000 RPM, so this is going at 1000 RPM, so omega. Have a little go at that. As a check, my gear ratio was 10/3. There's my little solution to it there if you want to see it. So what I've put there, the gear ratio is the product of number of teeth on the driven gears divided by the product number of teeth on the driving gears. I'm actually relating the number of teeth to the diameters when it comes for the sort of N1 and N2. They're actually diameters I'm using because that goes back to our basic relationship that we derived last week. Okay. So yeah, just be careful there that the number of teeth there are actually diameters, that's all. Gear ratio has to be 10/3. And then I can find the output speed. I've got the input speed given to me in the question, so I can find the output speed. I've actually got it in revs per second there. In the question states in revs per second, doesn't it? The answer, but in terms of revs per minute, 300 RPM. Okay, let's have a little go at question 8. So I'll quick go with this. This has got a simultaneous equation, very elementary simultaneous equation. I want to show here this one, and I want you to go at question 9 if you would. So the axes of 2 gear wheels of a spur gear are 250 millimeters apart. So we've got a geometrical constraint here. If one wheel rotates 3 times faster than the other, calculate respective pit circle diameters. So slightly different question here. So they're 250 millimeters apart. That's a geometrical consideration in between there and there. Gear ratio. So what do we get? We've got to find the diameter in this particular case, and I've got the gear ratio. So we know that G is equal to 3:1. So we can use this relationship here then. We've got to find diameter in this particular case to write it as G is equal to the dB over the dA. So I can rearrange that if you want to get dB, so just transposing the equation here. And I know in this particular case that the gear ratio is 3, so what I've got is a little relationship between gears A and B here from the information of the question. I'm trying to find diameters. I've got two diameters I don't know at the moment, but I've got a relationship between them. So I've called that equation 1 here. So I can't solve that at the moment, not enough information, but because of the geometrical constraint, I can actually form another equation. So there's a second equation I can form here. If I step 2, I know that the diameter of gear A added to the diameter of gear B, all divided by 2, is equal to the centre distance, c, which of course we know in this case. So I could rearrange the equation and I can get a relationship for the dA and dB again. So dA plus dB is equal to 2c. But I know c is 250, so dA plus dB is equal to 2 times 250. Call that equation 2. So now I've got two equations, both got the same unknowns, dA and dB in them. I can now solve that. Step 3, I'm going to substitute equation 1, I've labelled it as, into equation 2. You do the arithmetic on that. So you're going to take this expression, dB is 3dA, and you're going to put that in for dB here. So you're going to replace the dB with that expression and then rearrange as required. You do that, see what you get for dA first of all, and then you back substitute to find dB. Just give me my dA. So my diameter A is equal to, I get value of 125 millimeters. And then back substituting for B. Okay. It's a full solution anyway there. It's another solution. Okay, so yeah, I'd like you to have a little play with question 9, if you would, in the week. You've got two axes of two wheels, spur gears here, are to be 200 millimeters apart, so you've got some information to the geometry. One wheel is rotating 4 times faster than the other wheel. They've given you a module of 2.5. I won't use that yet. We've got to find a number of teeth on each of the wheels. So I'll give you some hints in the question, try and take you through the process. So the first thing you want to try and do is to state the relationship between dA and dB. It's given in the question. You've got the gear ratio effectively given for you there. And you can call that equation 1, a similar kind of way we did the previous question. And you've also got, in step 2, the centre distance formula that you can use. And again, you can find a relationship between the dA and the dB. Solve simultaneously as we've done. You'll find your diameters, and then noting the module is given in the question, you'll be able to find the number of teeth on gears A and B. So that's a little process through it. Okay, so can I leave question 9A with you? Those questions were predominantly looking at gear ratios and finding out velocities, number of teeth, all that kind of stuff. I want to go on and look at the calculation for torques and powers with gear trains. We're talking here about coaxially mounted input and output shafts. I just repeated this diagram you've seen many times now. This is called a coaxially mounted input and output shaft. I'm just trying to say that the input axis and the output axis are in the same line. Okay, so they don't have to be, but the gears we're going to look at now, they're all going to be of that format. And then going back from the relationship we've considered when we're talking about, the radius of gear A added to the radius of gear B, it is the centre distance, and we can put that in terms of diameters, then we could actually write a relationship in terms of diameters for a coaxially mounted gearbox arrangement. In other words, the dA added to the dB, think of that as RA added to RB if you want to, is equal to the DC added to the DD. Again, it's the radius. So although I'm talking diameters, it kind of equates to the radius. It's the radius of gear A added to the radius of gear B must be the same as the radius of gear C added to the radius of gear D if it's coaxially mounted. And I just put that in terms of diameters because we normally use diameters. Okay, and also if the pitches are the same on the gears, then we can write the relationship in terms of diameters. We can just write it in terms of number of teeth. We know this relationship. We've used it many times now. So instead of having dA dB equals DC dd, we can write NA plus AB is equal to the NC plus ND. So same equation really, but just in a different quantity there, number of teeth. So that's kind of equations we can use. And I mentioned this one earlier. This is to do with the modules being different. You can have different modules between the gear trains here. So A and B must have the same module. We're talking really pitches here. So we can write the expression for the geometry, if you like, of the centre distance of gears A to B as the number of teeth on A multiplied by the number of teeth on B multiplied by the module of those teeth. They have to be the same modules in both cases, and on the right hand side the modules for C and D, they have to be the same, but it can be a different module to A and B. So again, we can write the right hand side in a similar format, and again it's related to center distance but in a different form here. So again, that's a relationship that can be useful in some of the questions you'll see. So if it's okay with you, I'm going to put the solution to question 11a on the video, and you can just browse that at your own time. It's very similar to what you've already done. It's just bringing in this equation here into play because the modules are different between the teeth here. Here's the solution for question 11a. In a reduction gearbox with coaxial input and output shafts, it's required to have the gear ratio of 8:1. So our gear ratio, GAD, I've shown it here, is 8:1. Gears labelled A and B in our diagram, shown here, have 18 teeth and 72 teeth respectively. So number of teeth on gear A is 18, number of teeth on gear B is 72. Both gears A and B have a module of 3. So the module M1 I've shown here is 3. A second pair of gears, labelled C and D in our diagram, shown here, have now a module of 2. M2 is 2. We've got to determine the number of teeth on each of the gears. That's on gears C and D. So step 1, we've got to consider the velocity ratio or the gear ratio. GAD I've labelled it as here. And don't forget that's the product of the number of teeth on the driven gears. B and D are driven gears here, divided by the product of the number of teeth on the driving gears, A and C. Inserting our values, the gear ratio is 8, the number of teeth on gear B, 72, on gear A, 18 teeth. We do not know the number of teeth on gear D and C because we're trying to find those. Simplifying the right hand side there, that becomes 4ND upon NC. Finally, rearranging for NC, that's now equal to 4 multiplied by ND divided by 8, or 0.5 ND. Call that equation 1. Step 2, we're going to consider the geometrical constraints of this gearbox. And because it's a coaxially mounted gearbox, the centre distance between gears A and C must be the same centre distance between gears C and D. So writing that in terms of number of teeth and module, on the left hand side we've got NA added to NB, all multiplied by the module of gears A and B, and that's equal to NC added to ND, all multiplied by the modules of gears C and D. Inserting the number of teeth for gear A and B and the module of gears A and B, that's equal to the number of teeth on gears C and D added together and multiplied by the module of those teeth, which is 2. The next two lines just simplifies the equations, with the final equation being 135 is equal to NC plus ND, and I've called that equation 2. We're now going to substitute equation 1 into equation 2. So equation 1, NC is equal to 0.5 ND. So there's the 0.5 ND inserted for the NC in equation 2. Now we've got a simple equation with just one unknown, ND's unknown. So again, evaluating for ND, ND is equal to 90 teeth. Back substituting the value of ND into equation 1 above, we find that the number of teeth on gear C is 45 teeth. I'll let you review that solution at your own pace. So let's talk about torques in gear trains. Figure 10 shows a gear train where we've got an input shaft, this is shown over this side, left hand side here, and an output shaft. And this C notation here is called something called the casing or hold down torque, you'll see in a moment. What we're showing here is an input torque applied to the shaft, Ti, they've labelled it as here, and we've got the angular velocity of the shaft. Notice that they're going in the same directions. Ti and the angular velocity will go in the same directions. On the output shaft up here, the angular velocity on the output shaft is shown as omega naught here. And notice that the output torque is going in the opposite direction. You can see that T naught goes opposite to the angular velocity. And what you've got here is a kind of balance. If you kind of think of what's going on here, so the torque and the angular velocity for the input go in the same direction. But if the angular velocity on the output is the same as the input, shown in this diagram, the torque will be in the opposite sense, and that's because that's an inertia effect from the output. So imagine that a motor is connected to the input, driving the input shaft, so Ti is being driven and the speed there is driven from the motor. It goes through our gearbox in this center block here, and the output is going to the whatever it was driving, a machine tool or whatever. And the reason why T naught goes in the opposite sense is because of the inertia effect of that load. If you imagine you want to twist it in a clockwise direction, the resistance to that twisting would be going in anti-clockwise. There's an inertia effect from the output. The output machine tool. It says, I don't really want to move, you're going to force me to move, so I kind of resist you with an opposing torque. So that's why it's going in the opposite direction to the angular velocity on the output, because that's a reaction torque. That's an applied torque on the input and a reaction torque on the output. Notice in the next diagram, adjacent to it, we've got again the input torque and the angular velocity and the input going in the same direction. Now we've got the angular velocity going in the opposite direction to the input angular velocity, which can be fine. We know that from a gearbox we can have that. That can occur because of the configuration of the gears. But notice again that the torque on the output is going in the opposite sense again to the angular velocity, because again that's the resistance to the motion. The shaft wants to drive anti-clockwise, so the resistance is a clockwise couple. So when we're analysing torques associated with gearbox, we have to think of these two configurations. So Ti, TO and TC, they're called external torques that are being applied. The TI is in the same direction, shown rotating with the omega I, but notice that the T naught is in the opposite direction, always it will be, to the output angular velocity. Okay, and that reason why we need to know that is because when we're looking at the torque on the casing, or sometimes called the holding down torque, sometimes TH is used in some textbooks, we obviously need to get the direction of our torques correct to find out what the casing torque, that's the reaction torque on the actual gearbox casing, it's keeping the whole thing stationary. We need to know the direction of the input and output torques to find out the direction and the magnitude of the casing torque. So torques we've not considered before, and that's a new aspect to what we're doing. And also we need to consider the power requirements as well. You've seen this equation, P is equal to T omega. And again, I'm using angular velocity omega here, and notice in equation 13 I'm using the capital omega, because again we can use interchangeable units here, revs per minute in our radians per second, in this particular equation. What I'm showing you here is the power output and power input. So if we're assuming 100% efficiency, then the power output must be the same as the power input, and that's what the T omega is showing. That's a power input and the power output. When we add them together, and they must equal to 0 if we've got 100% efficiency. Okay, and again the direction of the omega i's and the omega naughts and the direction of the torques account for the senses in equation 13, you'll see in a moment. This is the equation for the holding down torque. So what I've got here are three torques applied. We're always going to have an input torque to the shaft, so Ti. We have an output torque, which is always going in the opposite sense to the output speed direction, my Ti, my T naught, and we'll always have a holding down torque or a casing torque, which is a TC. And for equilibrium condition, if that's going to balance, if that system is going to stay stationary, as it's, the actual casing staying stationary, then all those torques must equal to 0 for equilibrium. And the TC, as I said, is sometimes called the holding down torque in some textbooks. And the final equation is the efficiency of the gear trains. Now if they're 100% efficient, as we said on the previous slide, then the PO is equal to the PI. But if you do have an inefficiency, which you sometimes do have, then efficiency is given using the question, might be 98%, 90% efficient, whatever. And the efficiency relates to the output power over the input power. Obviously output power is less than the input power, and you can write that efficiency equation if you want to in terms of the T omega equation as well. It says that you can use either RPM or radians per second in this equation because you're really talking of ratios here between the speeds. So you can get away with using RPM, but be careful in some questions, you do need radians per second.
Okay, question 1-2. A gearbox powered by a directly coupled electric motor is required to provide a minimum of 12 kilowatts of power at the output to drive a load at 125 RPM. So in other words, the power at the output, that will be at D, is going to be 12 kilowatts. And the output speed at D in this case, is equal to 125 RPM. The gearbox used consists of a compound gear train, as shown in the figure, which has an efficiency of 96%. So the efficiency is 0.96. We're given a number of teeth on the gears. Gear A, shown here, connected to the motor, has 12 teeth. Gear B, shown here, has 30 teeth. Gear C, shown here, has 40 teeth. And gear D, shown here at the output, has 72 teeth. So we're asked to calculate, first of all, the gear ratio. Secondly, the electric motor shaft velocity, which we can find when we know the gear ratio. Because we've got the output shaft speed, we can find then the motor input speed. And we're also asked to find, in part 3, the power required from the electric motor. And in part 4, the hold down torque. Answers are shown in the brackets below. Now, in regards to part 4, related to the torques, in the question we're given the output power and the output speed. So whenever I'm given that kind of information, I naturally think of the formula P is equal to T omega. Power is torque times angular velocity here. But of course, don't forget the angular velocity in that equation is in terms of radians per second. But essentially, rearranging the equation, I can find the torque at the output. So I'm going to let you attempt this question and try and calculate the answers for parts 1 through to 4.
The solution. And I'm going to talk you through this here. So taking the information from the question, the output power from the gearbox, I've called that PO, is 12,000 watts or 12 10 to the 3 watts, 12 kilowatts. And the output speed of the gearbox, omega D, I've called that as 125 RPM. So that's all to do with the output of the shaft there. What I've also done is put the output shaft in terms of radians per second. So if you like, I will need that in a moment. Okay, so we've got the output power, we've got the output speed. We'll be able to find the output torque if we need it. And we've got the speed in radians per second. They've given us the gearbox efficiency in the question. So gearbox efficiency is given as 96%. Don't forget we always use a decimal there, so that'll be 0.96. And a number of teeth were given on each of the gear teeth. So number of teeth given up there, aren't they? So we can just write them down here. So on gear A, number of teeth is 12. Gear B, it's 30. Gear C, 40. Gear D, 72. Just reading that directly from the question. The first part of the question is fine. We want to find the gear ratio. So we've got a compound gear train. We can see that A is driving B and C is driving D in this case. I can find the gear ratio quite easily using my number of teeth on the driven gears or the number of teeth on the driving gears, cancelling down to my fraction, or 4.5 to 1, whichever you want to write. Okay. And then it wants us to find the electric motor shaft speed. So the electric motor shaft speed, that's the input shaft speed. And again, we can find that from the gear ratio. So parts 1 and 2 are no different to what we've done before. That's really the same kind of thing. Okay. So my speed of the motor, I've called it speed A there. Yeah, 562.5 RPM. That's my motor speed. Also put that in radians per second as well there. Didn't ask us for the output direction, but we can use velocity arrows. We can see here that it's going to be negative, positive. So Okay, so there's nothing different in that what we're doing than what you've done already. But let's look at the next bit where we've got to calculate the power required from the electric motor and also this hold down torque. And again, really, once you've seen a few of these, they are quite similar in their approach here. Okay, so calculate the power output from the electric motor. Well, we know that the efficiency is given in the question as 0.96. So we've got a formula for efficiency. Efficiency is the output power divided by the input power. So we've got the efficiency given, it's 0.96. We've got the output power required was 12 kilowatts, so that's 12,000 watts. So I can find the input power, just rearranging the equation. Okay, so for 96% efficiency, the input power would be 12,000 divided by 0.96, so 12.5 kilowatts would be the input power. So once the power at the input, that's how we find it, using the efficiency. Obviously, the efficiency 100%, it would be the same as the output, but there often are efficiencies in these questions to consider. And then finally, it wants me to find this hold down torque, TC, sometimes called a casing torque as well. So for this, we're going to use this equilibrium equation where the input torque added to the output torque added to the hold down or casing torque must equal to 0, which is true if the system's not accelerating. So when it's in sort of steady motion, this must be true. And you might say, well, why do you need to find all this? Well, if you want to find what bolts, for example, to hold the motor on with, this is one of the things you need to find. You need to find the torque, and then you can find the forces on the bolts, and you can find what size of bolts you need. So this is kind of where you need to know what the casing torque is. It's keeping the motor in position if these other torques are applied to the system. Well, as I said, whenever you've got powers, whenever you've got speeds, think of the formula P is equal to T omega, and that's the one that sort of always brings to mind when I got this kind of information. So the P is equal to T omega is a very useful equation, but just remember that that omega has to be in radians per second, or else you will get the wrong answer if you use revs per minute in that equation. So that's what I've done here. I've worked out my input torque, Ti, so it's the input power divided by the angular velocity at the input, which is in radians per second. So that gave me a value of 212.2 Newton meters. That's the input torque. And doing the same for the output torque. TO then, output power divided by the speed at the output. So 12,000 was the output power given to us. 13.1 was the radians per second speed. So 916 Newton meters is the output torque. Now it wants to find what is the hold down torque, what's the TC in this particular case. So we know from the previous calculation that the input speed must be input speed's direction and the output speed direction are in the same sense. We got that from our velocity arrows. So that will mean, this is where we've got to be careful, the input torque goes to the same direction as the input speed. It has to, because that's what's generating that speed, but the output torque will go in the opposite sense to the output angular velocity. So we need to be careful of that sense of the output torque. It's all dependent on the speed of the output shaft. So in this particular case, putting the equation down, the Ti plus the Tc plus the To, we need to be careful with the signs. If the Ti is considered positive, so positive in the clockwise direction of 212.2 is the input torque, the output torque in this case will then be a negative value, negative 916. So be careful of that. Going back to our previous slide, we worked out our torques there. Okay, I'm just using those torques, but I'm making that 916 negative. Why? Because the output torque sense is opposite to the input torque. I'm trying to find the TC. That's the whole point of this exercise, is try and find what this casing torque is. So what I'm going to do is rearrange the equation. This we transpose the equation to find TC. So just transposing, I get 704 Newton meters. Now I know the torque on the casing. If I know the distance between the bolts that are holding the motor in place, I can find the force, tension force on the bolt. I can then design my bolts and secure my gearbox to the ground. What I would like you to do, I'll give you another exercise here, is to have a go at question 2T as well. It's kind of very similar to what we've done. It's slightly less work to begin with because they've given you the gear ratio straight away, so you don't have to work out the gear ratio in this particular case. But the rest of the calculation is similar to what's shown on question 1T. So if I could leave you with that, as well as as the other question I gave you, it will give you a nice bit of practice on gears in the week, and then it's setting us for what's coming next week, because next week is quite difficult. If you think this is difficult, well, next week is I think is a bit more difficult than this. More so conceptually though, not numerically, not mathematically. It's more difficult, but conceptually, it's a little bit more difficult to understand what's going on with epicyclic gearboxes. But a lot of the underpinning techniques are here with us now. What we've got here, a little bit of generating equations, the using the modules and so on to work out dimensions, all that kind of stuff is going to be with us next week.